we realized that this barrier to entry for MLIP models, this is really crucial for the adaptation also in applications, because also you can only improve on those models if you actually see how they fail in real life applications. But if nobody uses them in real life applications because it's too difficult to use them, then that's an issue, of course.
Hi everyone, welcome to Let's Talk Research, the official InstaDeep podcast where we dive into cutting-edge AI research and the stories behind it. My name is Bora Gulola, I'm a research scientist here at InstaDeep.
And I'm Massimo Bortone, I'm also a research scientist at InstaDeep. And today we will be talking about machine learning interatomic potentials, or MLIP for short. These are models that are being used for molecular simulations, and here we will be talking about how they compare to classical methods and how our own work at InstaDeep is making them more accessible to the wider community, for example, through our own MLIP library.
Joining us today, we have two members of our Atomistic simulations team. Team lead Jules Tilley and lead engineer Christoph Brunken. Welcome both.
Thanks for having us.
Very happy to be here.
Right, Jules, so I've known you personally for a while. I know you have a very interesting background. Could you explain how you got into working for Atomistic simulations?
Sure. It's not exactly straightforward, actually. I started my career as a management consultant. And after about 3 years of restructuring banks, I realized it wasn't necessarily the most exciting thing I could do. So I joined a PhD in quantum information theory. And from there, building research and moving companies, I ended up at InstaDeep, setting up a team to look at machine learning for anything that has to do with quantum mechanical problem, and in particular, quantum chemistry. So how to solve for properties of molecules.
Right. That's quite a journey.
And Christoph, you were obviously heavily involved in the MLIP project. How did you find yourself on the project? What was your journey to it?
I've been working on the MLIP topic at InstaDeep for about 2 years, I think. And when we decided to create this MLIP library, I took on the technical leadership role in the project. My academic background is a PhD in quantum chemistry, and I also worked a bit as a data and ML engineer. So I think it's a very, very natural kind of combination of those two interests. And my main tasks on the project were guiding the design and the implementation work, and also overseeing the whole release process. So really making sure that that we do not only meet our technical standards, but also that we meet the needs of the research community. Because first and foremost, we think of the MLIP library as a user-friendly platform for MLIP models. And this should really serve two purposes in our minds. So one is that we want to have a tool set for scientific researchers that want to apply those MLIP models in an easy way to solve like real-world problems. But also at the same time, we want to have a framework for ML developers that would like to add new models and integrate them very easily with tools like molecular dynamics simulations, for example.
Absolutely. And so taking it back a step here, why is it important to be able to model these systems? Why are essentially atomistic simulations important?
Well, I mean, you can take it very broadly, and you think of all of what we do is chemistry, essentially. And the idea is the better you can model specific molecular systems, the better you can design or forecast what specific molecules are going to be able to do. And so that has a very wide range of application. You can think about, obviously, the entire pharma industry, drug discovery. It's all molecular interaction, but it goes way beyond that. It's all of the materials we interact with on a day-to-day basis, all the chemicals we interact with, and the way we produce and design them. So to that extent, anything that has to do with modeling these properties is extremely wide-ranging.
Yeah, absolutely. And I mean, coming from an MD background, so I did my PhD doing lots of MD simulations, classical force fields. There was always this question of kind of, okay, we're seeing this behavior, but is that actually what happens in solution, right? Does this protein behave in exactly the same way in solution? How do MLIP models factor into this basically? What do they improve upon?
Mm. So I think the main aspect here is that they solve a big trade-off in computational chemistry. So computational chemistry as a whole is really about understanding molecular systems and understanding how they behave. And this is also very important. For example, you want to predict forces of atoms in molecular systems, and this is needed for molecular dynamic simulations, for example. And in computational chemistry, you do have some methods that really take quantum mechanics into account. So really from a first principles perspective, they describe the quantum interactions of the atoms. And there are some methods that rely upon this, and they can be very, very accurate. But the downside is that they have a very high computational cost attached to them. And then on the other hand, there are some other methods that are very simple and they are very fast. For example, for large protein simulations that you talked about, we typically use empirical force fields like AMBER or CHARM are some examples or some popular ones. And these can be very, very fast, but they are not very precise at describing the forces, for example, but they are not at all really able to grasp the quantum nature of the matter. And I like to think of MLIP as really combining the best of both worlds by being a lot faster than quantum mechanical methods like density functional theory, for example, but also having an accuracy that is very, very similar to those methods.
Right. So maybe let's dive a bit deeper into this point. So the library, the MLIP library that you developed includes models like MACE, NeckWhip, VisNet, I think. Could you explain maybe, it's been quite a big few years for this whole field. It literally exploded. Could you maybe explain how these models compare to like classical methods and why people are so interested in these machine learning models?
Yeah, I think it's interesting to talk a little bit about the field and how it developed. So initially, it was a field which stemmed from the idea that quantum mechanics is too complex to solve computationally. And so people have started using empirical functions. Classical force fields are just the simplest one. And then people have started building more complex functions, like things like Gaussian processes recently, that were very focused on solving a specific chemistry problem. And if we look back at sort of the 2017-2018 period, we've seen a boom of new ideas, new models, which are based on graph neural networks. So you encode the molecule as a graph, and you basically use machine learning technique to spread the information on the graph into a specific function. And we've seen methods like there was SNET initially, and that evolved into NeckWhip, which is driven by Simon Basner's team and is now working for Google. And these ideas have evolved into sort of more a wide range of models. We can talk about MACE, who was developed by Ilyas Badaria from Cambridge, and VisNet that was developed by Microsoft as the one that we're looking at. But there are dozens of these models. And the idea really is to try to have an arbitrary manner to construct as complex as we want a function on a molecular graph and learn from it. And so that gives us a lot more flexibility than these classical force fields, which are simple, empirically fitted functions. Because of this, we can be very tunable in the way that we approach the problem. That gives us this ability to say we have a specific degree of efficiency we want to resolve this problem with, and so we can tune the level of accuracy that we want to achieve. And so therefore that creates a tool which is very versatile, and it's in a way very useful, as we can basically check, like select a specific problem we have in the quantum chemistry space, and then create the model that we think will be the best to manage this trade-off between accuracy and speed.
Yes. And I think there's also now, with the advent of really large data sets for this problem, which really wasn't the case up until a couple of years ago. But now we're talking about data sets with hundreds of millions of data points. Am I correct? like almost
yeah,
25.
that's true. Exactly, like the Open Molecules 25 dataset, for example, that was recently released by Meta. That's definitely a game changer in this field in terms of datasets. Because maybe what's important to understand is that what type of data do you need to train these models, which is accurate force and energy data for a wide variety of different molecules. And this, as you said, like it goes into the 100 millions in these data sets, and you need to compute these reference data at this density functional level theory. And I mentioned before that it's quite computationally expensive to obtain the data. So we are very happy that these data sets come out, and they make our lives a lot easier.
Yeah. And we'll actually talk about MLDFT in a later episode. So if you want to know how to accelerate DFT, stay tuned. But on another point, actually, I think so these MLIPs are sitting at an interesting intersection between accelerating quantum chemistry methods on one side and actually providing more accuracy for molecular simulations. So in a sense, you could develop these models for either or of these tasks, right? You could develop them for replacing quantum chemistry methods, or you can develop them with more of a improving molecular simulations in mind. How do you pick your battle?
So quantum chemistry is a ladder.
Right.
You have the fundamental methods at the bottom with extremely computationally expensive, extremely accurate. And as you go through every step of the ladder, you get less accurate and faster. Everything we're trying to do with machine learning in the space of quantum chemistry is go one step below in the ladder with the same cost as the previous one. And so if you think about MLIP as an application, we always strive to get first towards the accuracy of the ladder below. That's what we're aiming to get. We want to be comparable from a qualitative and a quantitative perspective so that the model is as useful as it can be. And then from that point onward, we try to compromise. We try to make it as fast as possible. And that comes through accepting further approximations, making the model slightly smaller, see what we can compromise with to get the qualitative results we want on specific use cases. But it also comes with an enormous amount of engineering. So a lot of machine learning and the speed in machine learning is very much dependent on how good your software is. And this is why sort of one of the focus of the team was primarily to look at how we can create a fundamental base software that allows us to deploy and test these models very efficiently.
And maybe quickly to add on that, this is also one of the design choices that we've made for our MLIP library, that we really prioritize this inference speed of the models, because this means then a very fast simulation speed. And we think that this is definitely something that will be crucial for a lot of applications, as Jules mentioned, because typically in these applications, you do not only do one specific simulation, but you do many calculations. Like in a simulation, you run multiple force evaluations in sequence, but also there are other applications where you run lots of simulations, even or lots of force evaluations. And so it's very important that the inference speed is very high, and this is something we are working on a lot for the MLIP library.
Absolutely. And it's kind of, from a practitioner's perspective, right? It's a dream come true. I have a faster force field that's more accurate than something equivalent, right? But then there's also this kind of opposing thing of, well, now I need to be able to use it, right? If I'm a practitioner, I'm not an ML developer, then there's often, you see these papers where fantastic results are shown, but then when you actually go and try to use the force field or the function, basically the scoring function, right, it's very difficult to actually get going. How did you go about thinking about kind of how you make models available for practitioners and ease of use, basically?
I think that one of there's two issues with the model you pointed out. The first one is making sure people can use them. The second one is, and this is what I want to talk about for a minute, is with all machine learning, we know when they work, we don't know when they don't work. And if you think about classical force field, density functional theory, all of these methods, they've been here for 100 years, right? We know how they work. We know when they fail. So us as well, but the community as a whole need to make a very concrete effort to validate these models and these approaches on as many different use cases as possible. And the space of all chemical problems is absolutely gigantic. So it's not a tiny effort. So what we strive to do is to not simply look at overall metrics. We have a battery of internal tests, which are very specific problems outside of our training set. So the models has never seen this problem before. And we validate our models on these tests. That is something that we aim to release in the next few weeks. And that really is here to measure how useful these models are. We need some proof points. One aspect of it that we are also working on is that we spend a lot of time collaborating with industrial partners and asking them what their problems are, and trying to solve it with our technology, and then see if it actually can be deployed on their problem. So I think that's this problem is a community-wide problem and it needs to absolutely be addressed.
You're hitting a really tough problem in terms of sort of how these new methods are being embraced by the wider community, because both molecular simulation with classical force fields and DFT have been around for a long time. So people are used to using not only the methods, but the software that has been developed to run these methods. So these are hard habits to sort of kick off and replace with new methods. And if the new method isn't faster or better or easier to use, people won't adopt it. So
yeah, I fully agree, and I think this is why we realized that this barrier to entry for MLIP models, this is really crucial for the adaptation also in applications, because also you can only improve on those models if you actually see how they fail in real life applications. But if nobody uses them in real life applications because it's too difficult to use them, then that's an issue, of course. And yeah, that's exactly like one of the main things that we wanted to achieve with the MLIP library, really to make these models accessible to everyone and not only to ML developers. We think that a lot of the other software that is around in the MLIP space has really been mostly tailored towards other MLIP developers. But we think that especially scientists that are in the field of computational biology, for example, that want to use these models, they should also have an easy access to the models, and this would accelerate the research in the whole field. And this is why we really concentrated on this for the library. And of course, we gave our best to achieve that, but also we are very dependent on feedback from the community, of course, in terms of what we can improve in future versions to make it even easier to use and even more comfortable to work with.
Yeah, and to people that might not know about this, it might sound like a very obvious thing, but actually integrating different tools like molecular simulation engines and your own developed force field can be a nightmare. So any tool that makes this easier, I think, is very welcome.
Definitely.
And the MLIP library definitely does that.
Yeah, and so thinking a little bit more about kind of your point on the community needs to stress test this, right? What do you think are the kind of requirements there in a way, right? Like what sort of systems do people need to test? What is the kind of level, the scale of kind of engagement that you need, right?
I think it's a very open-ended problem. There's already a few tools available out there. I can quote, for example, something called MLIP Arena. It tends to be very focused on materials, and it tends to be very focused on aggregate metrics. I think that first there's a need to establish this benchmark, and as a community, making sure that we all put an effort into it, put an effort in putting this benchmark out there and making them accessible and usable by different people with different models and so on. I think there's also some work that needs to be done from the perspective of sort of publications. I think there's a lot of effort that could be fruitful in systematizing the tests that people do when they publish new models, when they train new models. A very good example is the MES MP paper, which has 50 different tests, specifically mostly on materials, and that are very wide-ranging, and that that are done independently from the initial writing team, which means that they are very well tested and independent on systems that are not part of the training set. There are assessment that really shows where the model works, where the model doesn't work, and there's this overlay of effort by the community to try to understand why it works and why it doesn't work. And so I think that it is an effort that requires not only listing out all of these different systems and tests. There are thousands and thousands of them across materials, across chemistry, drug discovery, reaction analysis. And once these are listed, is making sure that there's a way to systematically test them, which is the bit that is a little bit lacking at the moment. I think the other thing is a lot of this field has been pushed mostly by academia. It's something we're seeing evolving over the last couple of years with players like Meta, Google getting into the field. But I think that there is also a large effort to be made working with the industry.
But you also mentioned that a lot of the kind of work in the field has been on materials, right? Can you elaborate a little bit more on kind of why that's been historically the case and kind of what the barriers are or where the work is heading in terms of biomolecular simulation?
That's a very good question. I think that there can be some potential reasons for that. I think one is maybe the research group that came up with these first models were more biased towards materials, crystal structures, bulk structures, and so on. I think that it is a possibility, and I think that that might be the reason why it evolved more towards materials. I think there's another reason, which is that we've really seen some early tractions for our MLIP models in the material space. Some very good results, some very useful results that drives the research in that space and the interest in that space. I also think that another issue is that the biomolecular space is absolutely enormous, and if you want to look at properties of biomolecules, you need to look. Obviously, you can always look at small molecules, but it only becomes interesting when you look at large systems and interactions of large systems. And here you fall into a bit of a computational problem, is that MLIPs are very fast, but they are still slower than classical force field. And so if you want to model an entire protein interacting with another protein and in solvent, you are talking about orders of millions of atoms here. Modeling all this still remains computationally intensive, and so you need to have the computational resources and you need to have the software that goes behind it and makes it efficient. And so that might be one of the reasons why the field has been more prone to looking at materials than about biomolecules. But I think this is slightly changing, and it's something that we want to push as well, simply because they are, first because MLIPs are getting faster. We see a lot of, obviously, new models, new methods to implement it. There are software like the implementation that we've developed, which is, it's somewhere between 4 and 10 times faster than what we can see in open source software at the moment. And so there's a lot of efforts that is pushed by the community to achieve these speed ups. But there's also sort of more, like that's just from an engineering perspective, but there's also more theoretical aspects and more methods aspects that are being developed. So models that are faster, distillation of the models, but also embedding methods where you just look at some part of the interest which are treated at the accuracy of MLIP, but the rest of the system use classical force fields. And all of these are helping towards creating sort of these opportunities in the biomolecular space.
Yeah, so I was just pointing out that the fact that most new MLIPs models are intrinsically non-local, and by that I mean that they aggregate information from long-range correlations to some degree, but they're much more.
That's debatable. I think it depends what we mean by local and not local.
Sure, but we can agree that they're much more or much less local than classical fields.
In terms of potential understanding of quantum mechanical effects, I would say yes. So, for example, in classical force fields, you typically only have these direct effects between atoms that are bonded to each other. And then you have, for more long-range effects, you just have dispersion interactions that you would treat, and you would have electrostatics, but also treated at a very approximate level, I would say.
Yeah. But this intrinsically makes them more scalable, obviously. Whereas the fact that models like Maze have message passing, first of all, and then they aggregate over different layers.
Yeah, it's also that the functional form is a lot simpler in
Yeah.
classical force fields, and so the number of parameters that you have is orders of magnitude smaller.
Yeah. Do you have an idea roughly what the difference is in the number of parameters?
Million difference, yes.
So that translates to a factor of 10
6.
maybe in speed? Or?
Speed. It depends. It really depends.
Yeah, it's not only about the parameters, but also about what type of functional form, what type of mathematics you have to evaluate. And this is also more complex in MLIP models compared to classical force fields, which typically just have these harmonic potentials, for example.
It's in terms of relative speed between the two, it's quite difficult to assess because it will depend on the underlying system. The MLIP model really depends on the structure of the graph that you're looking at. But there's also a question of hardware in the sense that MLIP models are tuned to work on GPUs. Most classical force fields will run on CPU clusters and so on. And so there's a good chance that at very, very large scales, actually, MLIP models might actually outperform classical force fields. But obviously at this runtimes, no one will be interested in running anything. At small scales, what we're seeing is that we are ranging between sort of within 2 and 3 orders of magnitude compared to density functional theory, for example, at small systems, because the scaling is different between the two. Even at small systems of up to 200 atoms, we are like roughly 10,000 times faster. And the bigger the system is, the faster we get. That gives you some order of magnitude.
So looking at the future, do you see a space where classical force fields are completely replaced with MLIPs, or do you see them working together?
So absolutely working together.
Right.
And in the sense that we cannot get rid of any of these methods. Like MLIP is just another tool in the battery of tools available for biophysical chemists and so on.
I think especially when you look at these very, very large protein complexes and you want to simulate them for quite some time, then you definitely need to look at these embedding methods, for example, that Jules talked about, where you'll have some parts of the system that will be treated with these MLIPs, for example, and they can be treated quite accurately, but you'll have a lot of parts of the system, for example, the whole solvation, that might be treated with a much simpler model, whether that will be the classical force fields of today or whether that will also be an advancement of these classical force fields. But I think this is surely how this will go for very large simulations.
Of course, this is something that people have been doing with empirical force fields as well, right? There's all these kind of hybrid QMMM methods, for example. So how easy do you think would it be from a technical perspective to plug an MLIP into this?
It's from a theoretical perspective, there's no real challenges for doing it. From a technical perspective, there are many challenges in the sense that we can take the theory of what was done for QMMM and port it into MLIP. And there's a few issues with that. The first one is we need to predict electrostatics to do electrostatic embedding. That's not something that current MLIPs are particularly good at, although we are seeing more and more methods that allows us to actually predict sort of charges and charge distribution accurately. That's one aspect. The other aspect is just the engineering of it. In the sense that we're talking about software that has been developed for 30, 40 years, and we are trying to recreate that into a new framework, and that comes with a number of issues that always join the software development. So
yeah, of course,
especially if you set yourself the objectives of also making it very easy to use for researchers, which is, as we said before, very, very important for us.
And you might be running your workload on different hardware as well, which increase the complexity.
But this is also a problem with kind of simulations, for example, that just use classical force fields and kind of classical software, right? For instance, if you want to run kind of a biasing scheme, a metadynamics simulation, using kind of the state of the art or the most commonly used software, it's still relatively fiddly to do it. And if you want to set up a QMMM simulation, ditto, right? There's always kind of challenges in setting up the system and getting it to behave and whatnot. So
I think this is an amazing point, because I think this is one of the advantages also of MLIP models that maybe nobody talks about so much, which is that they are much easier to use naturally, because they don't require all of these, like this bond topology, for example, that you need in empirical force fields. They are basically as easy to use as quantum chemical methods. Like they're more black box, let's say, than empirical force fields, I would say. Of course, the training process, that's where really the complex part is. But in terms of usage, naturally, they're quite easy to use, I would say.
And that's mainly because for classical force fields, you usually have this extra step of parametrizing the force field, right? Or
if you have, like, if there are some force fields, of course, that are pre-parameterized for you, but you still need to give it the bond topology of the system. And if there are some bond patterns, for example, that the force field doesn't know about, which often is the case, especially if you have metals in your system, then you need to reparameterize exactly those parameters. And then you don't really know how well they fit together with the other parameters. So it becomes quite technical to even set up a calculation and run it.
Yeah, I mean, I remember this. I had one project where I was trying to simulate a system that had a sulfated residue. It was a very esoteric modification on the protein, and there was very, very little literature on how exactly to parameterize this. So it ended up being a shot in the dark, right? We didn't really know whether it was going to work. But if you can essentially just plug in an MLIP model and just go from there, that's a much, much, much easier way to actually get the experiments running.
So we talked a lot about MLIPs and what to do, what we can do with them. The MLIP library, you released that in May, if I'm correct. It's been a couple of months now. I would like to ask, what has the traction been from the wider community? What's on your MLIP wish list, and where do you see the future of MLIP from now?
Yeah, so I think the reception so far has been quite good. We have gotten some good feedback on it, but we definitely plan to expand on it in the future. So definitely one of the topics that we mentioned earlier quickly was electrostatics. We definitely plan to add more advanced treatment of charge systems as well, but also just adding new models to the library in general, I would say. Also adding more pre-trained models that have been trained on these newer data sets that come out, larger data sets maybe that we've used before, reactive data sets, for example. Definitely these things. And then also we are always working on improving the performance in terms of simulation speed, as we talked about, because we think that's really crucial. So for example, by including faster backends that really optimize the mathematical operations that are required for these MLIP models. And yeah, of course, we are also very dedicated to just maintaining the library, right? So this means addressing bug fixes, of course, and small feature requests that come from the community, because we want to make sure that the library remains something that is very easy to use and that's also a pleasure to use for people.
Yeah, I was a beta tester on the libraries, and I was really impressed on how easy it is to use. It's really a couple of lines of code to get a nice visualization of your MD box simulation, which is really cool.
And that also comes together with this kind of idea of you need community feedback, right? Community validation. So part of that is obviously ease of use and kind of having a nice, clean implementation where everything works as intended. But it also means being able to reach a wide audience with it and letting people use the library. How are you going about doing that?
So I think there's a culture at InstaDeep, but in a large part of the ML community to open source as much as can be open sourced. And I would say in the MLIP field, it has been very important. I think a lot of people have been pushing for open sourcing models, open sourcing model structures and code bases, but also we can think about the gigantic effort that Meta has put together, releasing gigantic data sets, which is completely changing the potential for that community. We very much want to follow that trend. We spend a lot of time thinking about how accessible our library is. It's not for us. It's really to make sure that it is a useful tool for the community. And so our objective is to continue open sourcing what we're doing. We obviously have a lot of constraint in terms of code quality, code validation, and so on. So it might take a bit of time, but our effort is eventually to open source everything we produce with an aim to, as we said, making it accessible, but also engaging into a debate with the community on what is required, what functionalities are required, and how this code base can have as much of an impact as possible in the field.
That's all brilliant. Thank you so much both for coming and talking to us about all the fantastic work you've been doing.
Thanks for having us.
Thanks a lot for having us.
And to our listeners and viewers, if you're curious about everything MLIP and want to play with code and explore the world a little bit, make sure to check out our MLIP library. The link is in the description.
And don't forget to join us next month for our next episode, where we explore how to improve density functional theory using machine learning. Thanks, everyone.
Thank you.